Okay, so let me continue again on bearing capacity. So far I have what I have considered the jug is bearing capacity, which has considered only strip footing initially, and then it is extended to square and circular footing. And of course, I have also mentioned that when the soil is loose, how to incorporate. Then again I have mentioned if there is a water table, how to incorporate the effect of water table, that also I have discussed. I have also solved some problem in terms of dirt jug bearing capacity theories. Later on, to incorporate different effect of depth, then shape of the footing and inclination of the loading, we have discussed in terms of Meyerhoff's theory, and we have introduced so many factors. SC, SQ, S gamma, DC, DQ, D gamma, IQ, IC, IQ, I gamma, NC, NQ, N gamma, obviously it was there everywhere, and those things also I have discussed. And then when the load is actually supposed to be concentric, so that pressure will be positive pressure below the footing and uniform as far as possible, but in various situations where loading is not possible to apply through the center, or sometime moment is there, or there are some other loading, because of that there is a moment and vertical loading is there, and because of that resultant loading will be inclined. And if that happens, then generally footing pressure below the footing, pressure below the footing will not be uniform, it will vary place to place. And there are different situations I have shown that eccentricity will be measured in terms of width of the footing. If it is less than V by 6, then pressure throughout the width of the footing is positive, but one side will be little more, one side will be little less. And if it is exactly become equal to 1/6 of the width of the footing, then your one side will pressure will be 0 and other side will pressure will be little high, because of the moment pressure, moment loading and the compressive loading. And if the eccentricity become more than the 1/6 of the footing, then one side of the footing will become tension and other side will be compressive heavily. So, these are the aspects we have discussed, and how to find out that I have discussed. And another thing is that whatever pressure we get, ultimately that maximum pressure below the footing should not be more than the allowable bearing pressure of the footing. So, that has to be as a designer, one has to make sure that. So, again that is in terms of one-way eccentricity. Similarly, I have discussed in terms of two-way eccentricity also, when there is a when there is a rectangular footing and it is acting not on the center, it is 20 or 200 millimeter away from the y axis and again 300 millimeter away from the x axis. That means Ex and Ay both are there. In that case, how to find out the pressure are different, that I have given the expression, and you have to carefully use that second moment of area. You have to see that footing is rotating with respect to which axis. If it is rotating with respect to x axis, then you have to consider I x, and if it is rotating with respect to y axis, then you have to find out I y. And I x and I y, how it is different? Only the second moment of area expression is B L cube by 12. One is B and L, and only because of the change of the width, change of the axis, once it will become B L cube by 12, and when to change the axis it will be L B cube by 12. That is the change, has to be carefully noted. So, you have to see that the footing is rotating with respect to which axis. Accordingly, you have to choose B. If it is rotating with respect to x axis, then width parallel to the x axis to be taken as a base, and other dimension to be taken as a y. So, these are the various aspects we have discussed. Once again, like one-way eccentricity, what is the limit? That is 1/6 of the width of the footing. And similarly, when there is a two-way eccentricity, what is the limit? That is the area, in fact, that is called Kern. Within that area, if we apply the load, then your pressure supposed to be positive within the footing. Now, with this actually by and large I have covered what is bearing capacity related issues, but now after introducing Terzaghi's bearing capacity theory, I have taken one problem and I have shown how to find out the ultimate bearing capacity net and allowable, etc., and then how to take care of water table effect also I have shown one problem like that I have taken. But after introducing Meharov equation, I need to take one problem. Let me see the problem in the next slide. The problem is like this: we determine the ultimate bearing capacity of a rectangular footing of dimension 1 meter by 3 meter, resting on a deposit of sand with dry and saturated unit weight 15.5 and 19 kilonewton per meter cube. The dry unit weight is 15 and saturated unit weight is 19. An angle of internal friction of the sand is 30 degrees and footing is placed at a depth of 1.5 meter and water table is at the base of the footing. Use Meyerhoff's bearing capacity equation. So, that is the one. That means, what I have to do? I have to use Meyerhoff equation, that means Q ultimate will be equal to CNC, SC, DC and IC plus Q NQ, SQ, DQ, IQ plus 0.5 gamma B N gamma and your S gamma, D gamma, I gamma. So, this is the equation I have to use, and you can see now that C is not given. So, this component will be 0, NC anyway I have to, if phi is given, so automatically I can find out NC, NQ, N gamma, and SC, since it is a rectangular footing I can find out SC, since it is a place at a depth I can find out DC, and what about IC? Since it is no inclination is mentioned, that means a footing carrying a load means it is a carrying through the center. So, IC, IQ, I gamma will become 1. So, this effect of IC, IQ, I gamma will not be considered. So, this is the way I have to take, and another thing is while calculating this part and in this part you have to consider water table effect actually. So, footing is somewhere here and this 1.5 meter and this is also water table location. So, that means this unit weight part, that means this part will be affected by water table. So, this will be gamma, instead of gamma it will be gamma submerged will be used, and since the surcharge is above water table. So, this will be unchanged. So, these are the things to be noted. So, whatever I have discussed during Terzaghi's bearing capacity theory, that water table effect, here also I can take, though I have not mentioned, but water table effect will be same. Whatever was there in the Terzaghi, here also will be same. If instead of water table is here, then if water table was here, then what I have to do? I have to take effective gamma effective, that is a equation I have shown how to take gamma effective at B depth the full gamma, and when it is here it is half gamma almost, and in between I have to interpolate. That way we could have considered. If the water table was here, then what this will be unchanged, and this part I could have changed Q, instead of Q N Q I could have taken as Q gamma 1 H 1 plus gamma submerged into H 2 I could have calculated. So, that means water table effect will be whatever I have, the way I have shown, similar way to be introduced here. Only thing, new thing added here are these SC, DC, IC, SQ, DQ, IQ and S gamma, D gamma, I gamma. This has to be calculated and properly incorporated in this calculation. So, for this let me take a page and your footing is something like this. So, this is 1.5 meter and water table also here, and your phi equal to 30 degrees and corresponding NC equal to 30.14, corresponding NQ equal to 18.4 and N gamma equal to 15.67 and gamma equal to 15.5 and gamma saturated equal to 19. These are all kilonewton per meter cube, and since no inclination, I C equal to I Q equal to I gamma equal to 1, and your equation will be and since this part is water table not affected, your equation will be, and since C is not there, so your Q ultimate will be equal to this C part will be 0 plus Q here actually 1.5 multiplied by 15.5, this is Q, and NQ is actually your NQ is 18.4, and then I have to find out SC and DC. So, I will just find out SC equation. Actually, we have given SC equal to 1 plus 0.2 and then L by B. So, B by L. So, 1 by 3 tan square 45 degrees plus your 30 by 2, and if I do this value comes 1.2. So, that means I will put SC 1 point sorry, this SC is not required, actually SQ is not required anyway, because this part is total 0. I will not, just for showing, I just showed, you can I can just remove it. I will take now your SQ equal to S gamma actually, and that is 1 plus 0.1 1 by L B by L multiplied by tan square 45 degrees plus 30 by 2, and that comes your 1.1. So, this will be multiplied by 1.1 and d gamma. So, you have to find out DC again, I will not calculate. So, dq equal to d gamma, for this also dq equal to d gamma as given by Tajagi. I may have 1 plus 0.1 and 1.5 by 1 and tan 45 degrees plus 30 by 2, and if you calculate that it comes 1.26. So, this will be multiplied by 1.26 and plus half gamma, instead of gamma it will be gamma submerged, because water table here this zone. So, it will be 19 minus 9.81 half gamma, and B actually is 1 meter, half gamma, this is gamma submerged, gamma B, gamma N gamma is here 15.67 and your SQ, this SQ is 1 point multiplied by 1.1 multiplied by SQ 9 d gamma. So, yeah, SQ 1.1 and S gamma d gamma also 1.26, 1.1 and 1.26. So, if I do this one, then it will come finally 592.93 plus 105.23. So, this total comes 698.15 kilonewton per meter square. So, in this problem you can see that C value is not given, means you can assume phi given 30 degrees and C is given not given. We have assumed that C equal to 0, and since C is equal to 0, then this part becomes 0. So, I have not calculated SC SQ SC DC and SCDC I have not calculated. Okay. And so, I have calculated SQ S gamma or DQ D gamma, because these other two components are there. So, these two only I have calculated, otherwise whatever way it is given in the Meharov equation, I could have calculated SCDC. If C suppose given, C is given suppose 10 kPa, then this part would have not become 0. In that case, I could have taken C equal to this multiplied by NC, I could have taken this, and then SC DC all I could have calculated and multiplied and added. But since this part is not there, I have not shown here. Otherwise, I have applied the Meharov bearing capacity equation, and finally also I have applied water table effect also, because water table was here. So, because of that, in this zone where gamma supposed to be used, I have used gamma submerged. So, ultimately ultimate bearing capacity came 698.15, and of course, if it is asked for allowable bearing capacity, then I could have done some net ultimate, net allowable, then then final allowable. So, the whatever procedure I have shown there, same way I can do here. So, this is the way this problem can be done, and so the ultimate bearing. So, this is the application of Meharov equation. What is the way it is different? It was before only for phi corresponding to phi I have to determine NC, NQ and N gamma, and here additionally what I have to do, depending on the type of footing and depth of embedment and inclination of loading, I have to find out those factors SC, DC, IC, SQ, DQ, IQ and SC, DC and IC, and SQ, DQ, IQ and S gamma, D gamma, I gamma. So, all 3 components, 9 components, additional components to be, and those are empirical equations and given, I have also shown previous lecture. And here actually since C is 0, so first 3 components not involved. So, other 6 components are involved. So, I have calculated, so you can see here 4 in fact 1, 2, 3, 4 and IC, IQ, I gamma already 1 because of no inclination. So, 3, 2, 3 and plus this 3, 6 are gone. So, only remaining 4 are 3 and 2, 5 gone, only 4 to be determined. So, I have determined here and I have used here. So, so if it is a Tarjaghi bearing capacity, it could have been ended here. So, this is 1.1 and 1.26 because of what it came SQ and DQ. Similarly, if it would have been your Tarjagis bearing capacity here, actually it could have ended here, but I have added this one. What is that? H gamma and D gamma, these two parts are available, and to take water table effect, it is similar to your Tarjagis equation is taken. So, finally, the bearing capacity, ultimate bearing capacity comes out to be 698, approximately 700, and then you can apply your different factor of safety, etc., to find out the allowable bearing capacity. So, this is the application of Tarjagis bearing capacity. Let me take one more small problem where actually I have discussed about reduced width of the footing to find out the ultimate load carrying capacity of the footing, and you can see that determine the ultimate load which an eccentrically loaded square footing of 2 meter size with an eccentricity of 0.4 meter, and that eccentricity is given in one direction, can take when placed at a depth of 1 meter in soil with gamma equal to 20 kilonewton per meter cube, C equal to 15 kilonewton per meter square, phi equal to 30 degrees, and NC, NQ, N gamma is given, and ignore water table and use Tarjagis bearing capacity theory. So, here actually there are number of typos, actually and is spelling mistake and Tarjagis is supposed to be capital. So, I have done mistake here. So, let me see this problem. Here actually the problem is given it is of 2 meter square footing of 2 meter size, it is 2 meter by 2 meter, and eccentricity is 0.4 meter. So, that means the footing is, suppose this is 2 meter and this is 2 meter and eccentricity is 40 meter. So, what is the effective width? Actually that has to be the B dash will be B minus twice E. So, that means B was 2 minus 2 multiplied by 0.4, that means 1.2 meter. So, B dash is 1.2 meter, and so in that case your Q ultimate to be used as, I have mentioned Tarjagis theory is to be used and a square footing. So, 1.3 C N C plus Q N Q plus Q N Q plus 0.4 gamma B dash N gamma. This is the way to be used, and so you can see 1.3 C is actually is given as 15 multiplied by 15 multiplied by NC is given 37.2 plus Q is actually will be 1 multiplied by 20 multiplied by NQ is given 22.5 plus 0.4 gamma is actually here, water table is ignored. So, it will be same 20 multiplied by B dash actually to be used 1.2 multiplied by N gamma is given 19.7. So, here actually what I have done, I have calculated reduced width or effective width and then applied Tarjagis bearing capacity equation. So, from here I can get it will be 1364.5 kilonewton per meter square. So, if I want to find out Q ultimate since it is a one way eccentricity, Q ultimate will be 1364 multiplied by area of the footing will be 1.2 by 2. So, that become your 3275 kilonewton loading. Okay. So, this is only application of bearing capacity, only how to reduce the footing size because of the eccentricity, that is the application shown here. Next, one more problem. So, this is a 2 by 3 meter rectangular footing loaded with 2000 kilonewton at an eccentricity of 250 millimeter, and determine the maximum and minimum contact stress below the footing. So, this is the problem. You can see footing is something but loading is applied here. This eccentricity is 0.25, and this can be visualized as a concentric load, and there is a moment. So, moment become 2000 multiplied by 0.25 become 500, and this is 2000. P is P m equal to 500, P equal to 2000, and your footing dimension is, this is 1 meter and this is 3 meter. Two by 3 meter, actually this is 2 meter and this is 3 meter, and then your Q max will be equal to, you know that P by BL 1 plus minus Q max or minimum 6 E by B. So, here, so if you do that, you can see P become 2000 divided by 3 multiplied by 2, 1 plus minus 6 multiplied by 2.25 divided by B is 2 meter. So, if you do this calculation, you will get Q maximum actually 583.33. Similarly, Q minimum will be Q minimum will become, if I use minus sign, then it will become 83.33 kilonewton per meter square. So, either directly one can use this equation, or one can do this way: 2000 divided by 2 multiplied by 3 plus minus m actually 500 multiplied by y is actually here 1 meter, my by I will be this with respect to this axis 3 multiplied by 2 cube by 8. So, this way also, by using this equation, this is Q max or Q minimum. So, 2000 by area multiplied by m into y by b h cube by, sorry, this is not 8, this will be 12. This will be 12. So, by this actually whatever you get, and by using this also whatever you are getting, it will be same. So, I can either directly remember this equation, or I can remember the instead of remembering the equation, I can do in this form. That means, because of the compressive load, what is the pressure, and because the moment, what is the pressure. Because the moment pressure is my by I, m is calculated load multiplied by eccentricity, and y is maximum this distance, that is half the width of the footing. And what is I? The I should be, since it is rotating with respect to this axis, then I have to consider this as the axis, and then this will be base and this will be height. So, it will be 3 is the base, and h cube by 2 cube by 12, and then if I simplify this, it will come also same value 583 and 83. So, this is another application where actually when the footing is applied with eccentric load, then how to find out the maximum and minimum pressure, because this maximum pressure should not be more than the allowable pressure of the footing. So, this has to be calculated and checked, and so these are the various application whatever I have already mentioned, those things, and with this I will stop here. Maybe next class I will just one or two aspect of bearing capacity I will consider, and then I close the shallow foundation, and then I will proceed to the next topic. Okay, thank you.